Started section 4.5 last time, integration by substitution, and let's see, are we on 5 or 6? 5? All right. Let's take a look at number 5. What's your question, Dawson?
Are we going to have to use the property for 2x or whatever? You know what I'm talking about when we had trig?
Like a double angle property or something like that? Typically not. So take a look at this one and let's just go through it and we'll see. The trig identities that are most useful on a recurring basis in calculus are Pythagorean identities, reciprocal identities, and quotient identities. And you can get by with mostly only those. Even into Calc 2, my students in Calc 2 very rarely encounter any of the other trig rules where it's a necessity that they know that rule in order to do them. Those 3 sets of rules are pretty much enough to do what you need to do in Calc 1 and 2, okay? So if you're still rough on those, or if you don't remember them, I would encourage you to go back and to do that. The other thing I would encourage you to do is, if you have not already come and seen me about your antiderivative gateway exam, whether you have time to repeat it or not, I would encourage you to come and take a look at your old exam before you take your exam on Friday. Because if there is a common mistake that you're making, know about it now so you don't make it on Friday, because there's no redoing or repeating that test, right? Yeah. And you do have the opportunity to redo and repeat the gateway still up to next week, and that's fine, but know what mistake it is that you're consistently making so we don't repeat it, okay? All right. Okay, so we're taking a look at one here that does in fact have some trig in it. It says to find an equation for the function f that has the given derivative and whose graph passes through the given point. So the first thing we have to do is to figure out what the equation is that actually, has this derivative. And so if it has this derivative, that means we have to find the antiderivative to actually assess that this is its derivative. Does that make sense to everyone?
Yeah.
All right, so we're going to take an antiderivative of this function. So we need to do an integral on this, right? Now, secant squared is one of these that you do know the antiderivative for, or at least you should. Now, the fact that there's a 2x inside, which might have spurred your question, Dawson, doesn't really affect a lot because we have something called substitution. U substitution. So that's why we don't need to worry so much about double angles and things like that, because we can use U substitution. So our U can be the 2x, and then what would du be? 2 dx. Yeah, and now there isn't a 2 outside of secant in this problem, right? I should put a dx here to make it complete.
So you just put it in there? Take it out?
Well, what we do is we'll divide both sides by 2. So our dx, when we replace it, will be replaced by a 1/2 du. You can put the 1/2 kind of wherever you'd like. I tend to put it in front of the integral symbol because it doesn't affect what my integral is. It just tags along for the ride. So let me use a different color here. My dx right here, that green was not a good choice. Let's try again. Let's try blue. That's better. That dx gets replaced by the 1/2 du. Oh, there's a squared. I haven't actually done any antiderivatives yet.
Okay.
I was just rewriting, but I left my squared off. You're right.
Was there supposed to be a dx on that?
We put the integral symbol in, and when we put the integral symbol in, we put the dx in, yes. Yes. Okay, so is everybody good with where we are at this point?
Yes.
Okay. Now you're ready to take your antiderivative. So I mentioned it, and I'll mention it again. The 1/2 just comes along for the ride. You don't do anything with it. It's just part of the answer. However, we do need the antiderivative of secant squared, and somebody told me what it was just a second ago. It's tangent. So this is tangent of u. And then what else do we need? Plus c. Now, on the left-hand side, when we did the antiderivative of f prime of x, what do we get? That's f of x, right? The prime notation simply comes off. Now, unfortunately, it's not really f of x yet because we still have a u in it on the right-hand side, so we do need to change that. What should it say?
2x.
Yeah, it should say tangent 2x and then plus my c. So my general antiderivative is 1/2 tangent 2x plus c. But we are given a point, right? Pi over 2, 2. And that will allow us to figure out what in the world c actually is. The c on the end, all it does is it takes a graph and it shifts it up and down. Do you guys remember that from probably an Algebra 2 kind of course somewhere? that all of plus c does on a graph is shift it up and down. So we're actually isolating the location by plugging in the values to figure out what c is. That's what we're really doing. So we're going to plug in pi over 2 for x. And we know that when we do that, it will equal the number 2, correct? Okay, so starting with the piece on the inside, what is 2 times pi over 2? Okay, so it's pi, right? So this is tangent of pi plus my c equals to the 2. And I don't really need the equals over there necessarily. What is the tangent of pi?
0. 1. Which closer?
Which one is it?
0.
Is it 0 or is it 1?
Cosine.
It's sine over cosine, so it's 0. Yeah, it is 0. So this piece, right, well, I'm sorry. This piece right here is 0, right? And since that piece is 0, the 1/2 times the 0 is 0, and all I'm left with on the left is c, and so we find out that c is equal to 2. Once we know what c is, we have our function f of x equals 1/2 tangent of 2x plus 2.
Can I ask a quick question again?
Yes.
Well, okay, so where did the 2dx come from?
The derivative of 2x.
Oh, okay.
So what we're doing when we do our u substitution right here is we identify what u is, and then we take the derivative. And what really happens is when we take the derivative, we get du dx equals 2x, and then we multiply the dx to the other side,
You mean 2?
like that. Oops, I'm sorry. I didn't mean a 2x. Yeah. All right, let's try that again. 2, and then 2 dx. We multiply the dx to the other side. We just tend to not to ever write down the du dx equals 2 line. We write du on the left, we write the dx on the right, because that's where we're going to eventually need them anyway. Okay? So in the middle of this antiderivative, you're doing a derivative, correct?
Yes.
That's really what you're doing. Yeah. All right, let's find another one. Now, I mentioned this last time that this one's a little unique, and the reason it's a little unique is because looking at this, you could probably tell me what u should be. What should it be? Yeah, the part that's underneath the radical, right? The 2 minus x part is the part that looks like it's inside of something else. U is always this item that's inside of something else. Sometimes it's inside of a denominator even. But this is inside of a radical. The thing is, though, that if I let this be 2 minus x, the derivative is not the x plus 1. So this is the 2, and this is the dx right here. So this is all the same. It just ends up looking a little bit funny because I didn't get rid of the x plus 1 somehow. But you do have something else you can do.
Wait, what's 2x?
Why is it?
Is it negative 1?
Oh, because I'm moving too quickly and I'm not looking at my notes. How about that? Thank you. Okay. So I don't have, as of yet, a way to eliminate that x plus 1 on the outside with this u substitution step, right?
Yeah.
But I do have a relationship between x and u, don't I?
dx du?
The very first one.
Okay.
U equals 2 minus x. Yes?
Yes.
So
So x is equal to
X is equal to, go ahead, Garrett.
u plus 2, or negative u plus, is, you have to move the 2 over and then divide by negative 1.
Yeah, it's equal to 2 minus u. In other words, if I added the x to the other side and subtracted the u to the other side, I could solve that equation for u. I mean, that is for u, for x. I can solve the equation for x. Is everybody okay with that? Okay. Why is, are you, what's wrong, Luke? Okay, let me do it in a few steps then. We're taking this equation. Whoops, I didn't get that written very clearly. We're adding x, and we're subtracting u.
So why can't it be 2 minus x?
It is. U is 2 minus x, and x is 2 minus u. Those are two equations that are exactly the same. They're just written differently.
okay.
There's a reason, though. Okay, so we set it up originally so that this piece right here can be rewritten with u, correct? Okay, so this is now u, and I'm going to write 1/2 as the exponent instead of the square root. Everybody good so far? But when I replace x's with u's, all of the x's have to go away. All of them. So the dx at the end is -1 du, right? And this piece at the beginning, x plus 1, well, what is x? It's 2 minus u plus my 1. So this x gets replaced with 2 minus u. This 2 minus u gets replaced with u. And this dx, I'm using too many of the same color, red. This dx gets replaced with -1 du. I've made 3 substitutions in this problem. But I have everything now with u and no x's, right? Okay, let's clean it up a little bit, and I'll show you why this is a helpful step. So the part that's at the beginning, this part right here, is 2 minus u plus 1. What is that? 3 minus u. Then I have u to the negative, or sorry, to the 1/2. I have a negative du, so I'm just going to put my negative, you know what? I'm going to distribute my negative through here. Okay, I just distributed this negative. I don't know why it turned into, no, it did. What? That's right. Huh? What? Okay, so Chad, stop just a second and think about your question. Okay. Yeah. So the answer is actually yes, but also the answer is it doesn't matter, right? Yeah. So we have that negative. Oh, and I still need my du. Okay, is everybody okay with this line? I just cleaned things up. I distributed the negative. I cleaned up the addition in the front. You could.
Okay.
Put it wherever you want to. Eventually you're going to distribute it through because you're going to have to do that for your answer. So.
Cool.
Okay, here's the catch about why. You might look at this and say, well, how is that more helpful? I still have an addition. I still have a radical, basically. Why is it more helpful? Well, it's more helpful because the addition is not under the radical. And the reason that's helpful is because I can distribute the u to the 1/2 now to each of those terms. I can't distribute into the inside of the radical very cleanly or easily, but I can certainly distribute the radical, which is a single term u, to each of the other pieces now. So I can actually rewrite this as -3 u to the 1/2 plus u to the 3/2 du. Okay? Now I have 2 pieces. They're both power rules, and I can take their antiderivative. So, what's the antiderivative of u to the 1/2? Yes, Bryson?
Would usually 1/2 be negative? Because you distributed through the 1/2, the -1.
It's all multiplication. So think about what happens when you have a -1 times a 3 times a 4. Distribution distributes across addition and subtraction, not across multiplication. So the u to the 1/2 stays as u to the 1/2 because we've already distributed it through the addition subtraction part. Yeah. Okay. Okay, so the -3, I'm going to rewrite the -3. What do I get for the u to the 1/2 part?
It's 2/3 u to 3/2.
Okay, so the u becomes to the 3/2, and then we would divide by 3/2, right? So if you want to write divide by 3/2, more power to you. But you can also write it as multiplying by 2/3. Yeah? It's kind of nice, right? It's kind of a mess, actually, is what it really is. But I'm going to give myself a little more space. All right, so this is the first half, basically. What about the u to the 3/2? U to the 5/2.
2/5.
And then dividing by 5/2 is the same as multiplying by 2/5. And then what else do I need?
Plus C.
Thank you, plus C. All right, and then we're going to clean it up, right? There's not a lot to clean up, but there is a little bit right now. What do you see to clean up? Yeah, the -3 times the 2/3, which would just be -2. Somebody tried to tell me to do that just a minute ago, and I was holding you off. So this is -2, and it is right now, anyway, u to the 3/2. Plus, and then I have 2/5 u to the 5/2 plus c.
Goods and radicals.
Which, yeah, it's radicals, right? So I should be putting these in as radicals. So I have -2. I have a square root. But what's u?
Square root of u.
2 minus
It was 2 minus x. So this is the square root of 2 minus x to the third. Plus, and then I have a 2/5, and I have a square root of 2 minus x to the 5th plus c.
Now we have to find C.
We can't find the c on this one. Does anybody know why?
It's not given in that.
There's no points.
We're not given an ordered pair to find it for, right? Yeah. A couple things. The answer here is fine. If WebAssign doesn't like it, do you know what it might not like? Can you guess? They might not like the fact that there's an exponent on the radical part. So you might have to simplify it. So what would it look like if you had to simplify it? Like, I'm fine if you leave it here, but I do want you to think about in terms of WebAssign what you could do if you were checking it back of the book or if you were checking with a classmate or something. What else could you do here that actually would simplify this? Because it does actually simplify a little bit more.
So bringing 2x out of the first one.
All right, so the first one raised to the power 3, right, with the square root is like having a 1.5 exponent, agreed? So you've got one of them, that's 2 minus x, and then you've got another radical of the 2 minus x. The other one has the same feature, but it's 5/2, right? So 5/2 is the same as 2.5. So you could actually pull the 2 minus x squared out, and then you have a square root of 2 minus x. So just for fun, what else could you do? How about we undistribute? Factor? If you'll take a look at what's going on there, sorry, that's really tiny now, but I needed some more space. So if you take a look, they both have a square root of 2 minus x in them, right?
Yeah.
So you could factor out the square root 2 minus x.
Even though c doesn't.
We'll have the plus c on the end. It won't affect it. Yeah, it won't be part of the factoring part, basically. And then what else? Oh, and there's a 2 minus x, you're right. Let me put that in there too. And then what's left? Well, there's a -2 from the first piece. And a 2/5 and 2 minus x from the second piece. And then I have the plus c on the end. So that's where that plus c is going to go, Gus. And we could clean up what's in the brackets at least a little bit, right? I mean, it's not pretty or anything, but it does clean up a little bit. So you have the 2 minus x here. You've got the square root of 2 minus x out here. And then I've got, let's see, -2/5 x. And then I have a -2 and a +4/5. Do you know what that is? -6/5 is correct. Right, because the 2 is the same as having 10/5. -10/5. Yeah, -10/5. Okay, so that's another version of it.
Never mind.
So for clarifying one more time, I'm okay if you want to stop here. And if WebAssign's okay, then by all means, just push pause and try it and see what happens. But if it wants you to clean things up further, it might be expecting you to do some of the things that we just did following, okay? Good with that? You all right, Rachel? Oh, goodness. All right, couple more examples.
Where were you okay with this stuff?
What's that?
Where were you okay with this stuff?
When I boxed it in the blue, or in the red.
So with the powers.
With the powers, yeah. You do need to put it back in radical form, that's a for sure. I mean, even if WebAssign accepts it, I'm not going to accept it on your paper if you don't put it back in radical form, because however the problem begins is how it should end. If it begins in radicals, it should end with radicals, okay? Yeah. All right, evaluate the definite integral. Okay, so the last two examples are definite integral questions. So we don't have to just do the definite integrals in the cases where you've done them already. You can actually do definite integrals with U substitution as well, but there is one little caveat along the way. So I want to make sure that you're aware of it. So taking a look at this, can you tell me what it appears your inside function would be? 1 plus the square root of x. Indeed. So then, what would du be? Notice this is the same as having 1 plus
1/2 x.
x to the 1/2 is what this would be. So what would it be?
1/2 square root of x.
2/3 x.
Okay, remember we're doing derivatives and not antiderivatives, so be very
1/2
careful.
x and then
There will be a 1/2, and then there will be x to the
negative
-1/2. And if we rewrite this, that's dx then. If we rewrite this in positive exponent donation, I guess, or notation, I guess, it would look like this, right? Is everybody good with that?
Yep.
Compare that to the original equation. What do you see?
It's close.
It's close. You have the 1 over the square root of x and you have the dx, right?
So you pull
But what happens?
The only thing you don't have is the 2, right? So what do I do with the 2?
pull a 1/2, multiply it.
I multiply it to the other side. So I'm going to have a du, it equals 1 over the square root of x dx. So the 2 will become part of the outside of the antiderivative.
But 1 over x squared.
Hmm?
What about the square? 1 over square root of x.
Well, it's highlighted in red on my screen. Do you see it? All those pieces are the same as what I have on the right, correct?
So it's,
Yes.
So they get replaced with the du at the end and the 2 at the beginning.
Oh, okay.
Okay?
Because I did square root of x equal to u plus 1. I guess that makes more sense.
It makes it more complicated if you think about it with replacing it that way, yeah. Okay, we got the du at the end. Everybody good with what I have so far on the board? Okay, the part that I don't have now, though, is the part that's not highlighted, the 1 plus the square root of x squared in the denominator. How could I rewrite that? It would be u squared in the denominator, or how about
Du.
u to the -2 in the numerator,
yeah.
right? So this piece right here is u. It's squared, but it's in a denominator, so I'll pull it up to the numerator and make it -2. Yes,
What do we do?
the 1 and the 9?
Do we leave it there?
The 1 and the 9 are going to disappear for the moment.
Okay.
And here's why. There's 2 ways to do this. I'll tell you which way I'm not doing it. You can do it. It's nothing wrong. It just I feel like it makes things more complicated. The 1 and the 9 apply to which variable? X. Do you have X's in your problem right now? No. So you can't put 1 and 9 on. That is completely not okay.
So
All right?
you can't even write it there?
You cannot write it there. Now, if you want, you can figure out when x is equal to 1, what is u, when y is, or when x is equal to 9, what is u, and you can put those new values in. You can do that. I don't do it that way. Let me show you how I do it, and I'll explain why I like it better as we work. Is that okay? Okay. So what is the, just leave them off for now. What is the antiderivative of u to the -2?
Negative 1 over u.
Okay, so u to the -1 over -1, right? I still have the 2 in front. And I would have a plus c at the end. I don't actually need the plus c's because eventually I am going to plug in a 9 and a 1. Okay, so I don't really need that right now. But is this okay? And if I clean this up, simplify this, this would give me -2 over u. Correct?
Yeah.
But what is u? 1 plus the square root of x. And at the point when I have the x's back in, I'm going to draw my vertical bar and I'm going to put the 9 and the 1 there. Okay?
I'm still
Trying to follow.
The reason I like to do it like this is because it most closely resembles what we do when we don't have the 9 and the 1.
Okay.
At the end, we turn them back into x's, we put our plus c, and we're done, right? So at the end, we turn it back into x's, we put our 9 in where 1, and we calculate that, and we're done.
Okay.
That's why I do it this way. It's because I feel like it most closely resembles the other indefinite integrals. All right, so I have -2 over 1 plus the square root of 9 minus a -2 over 1 plus the square root of 1. So the minus -2, of course, is plus. What's the square root of 9?
3.
3. So I've got negative 2 over 1 plus 3, which is 4, plus the 2 over 2. 2 over 2.
Yeah.
All right, what is negative 2 over 4?
Negative 1/2.
Negative 1/2 plus 1, which gives me 1/2.
I have a question.
Yes?
So radical 9, is it always 3 or plus or minus 3?
It's always 3 because the radical's already there. The only time you put pluses or minuses is when you put the square root on. When the square root's already there, it's assumed to be what's called the principal square root, which is only the positive part.
Okay.
All right, we have one more example. You ready? What is a little bit awkward and weird about this one? And don't tell me it's got sines and cosines in it. That's not what it
Cosine
is.
That's 2x.
2x.
But it isn't just that it has 2x. It's that, say it loud, Chad.
They have different angles.
Right. One of them has x and the other one has 2x, which is a little different, right? Okay, so what we're going to do is when we have the 2x part, we need to use substitution, agreed? But when we have the x part, we don't. Yeah? So what we're going to do is we're going to use a property of integrals that you guys learned a couple sections ago, and we're going to separate this. Yeah, because half of it doesn't need use substitution, and the other half does. Okay, is everybody good with that?
Yeah.
Let's just do the first half, and we'll come back to the second half. What's the antiderivative of sine of x? Negative cosine of x. And we draw our vertical bar with the pi and the 0. So we write in here negative cosine of pi minus the negative cosine of 0. Well, minus a negative is plus. Okay, so what's the cosine of pi? Yeah, so I've got negative of negative 1 plus. What is the cosine of 0? 1. So this negative negative at the beginning is, of course, a positive, and all of this ends up being 2. Okay, so half of my problem is now done. And we're going to go through, I'm going to put pluses on everything because we've got the other half still to do, and it needs to be done with u substitution because I have an angle 2x. So what is my u? 2x. What is du? 2 dx. I don't have a 2 in my problem, so now what? Divide the 2 to the other side. So my dx gets replaced with a du and a 1/2 at the beginning. My cosine is still cosine, but my angle inside is u, because 2x is equal to u. What am I going to do with my 0 and my pi? Not put them in there. Yeah. I need to leave them off because the values 0 and pi apply to x and not apply to u. So I wait. Okay, cool. So I've got 1/2. What's the antiderivative of cosine of u?
Sine.
Sine of u. But what is u?
2x.
2x. So I've got sine and 2x, and at the moment that I put the x's back in, I can put my bar with my limits on x, pi and 0. So now I have 1/2 sine of 2 pi minus 1/2 sine of 2 times 0, which is 0. All right, so what is the sine of 2 pi? It's 0. What is the sine of 0? It's 0. So my answer of 2 plus 0 then would just be the 2. But it does have to be split up. If those values had not been pi and 0, of course, we wouldn't necessarily have gotten zeros. So we don't know that going into it, okay?
Why don't we have